Right, well, welcome to the Halifax and District Amateur Radio Society. Tonight I'm going to give a little talk on a very popular and relatively new kit from Kanga Kits, which is the Rock Rose direct conversion transceiver, which is this little beast here. Relatively new kit. It's an old idea with a new spin on it. So if any of you have been within interesting QRP and can think back to the early 2000s when Reverend George Dobson was alive and kicking, and the Rockmite came out, which was very much like one of these things, a little tiny direct conversion transceiver, crystal controlled. And what Paul has done at Kanga Kits is to buy all the PCBs and all the bits and pieces from a company in China who were making these things, and started to part up a different kind of kit with some improvements on it. And this is what this is. It's a Rockmite with a lot of other bits and pieces stuck inside it as well. It's essentially three of Kanga's kits put together. You've got a transceiver, you've got an audio notch filter, and you've got an Iambic Keyer, which is quite clever. So let's have a little look at what this thing actually is. If you remember back to my talk on the little roux, the receiver, this block diagram was relatively simple. We simply had the bandpass filter, the mixer, which had a little oscillator on board it, and then we had the audio amplifier, and out we came. This is a little bit different because we have to transmit and receive on two different frequencies with a direct conversion transceiver. One of them is the transmit frequency, if you've got the net frequency. Then to be able to hear that frequency in the receiver or the other person's transmission on that frequency, we have to offset the local oscillator on receive so that we get a 700 Hz or thereabouts tone difference, so we can resolve that in the receiver as the CW tone. So what we've got, it's all built around this Iambic Keyer. This Iambic Keyer drives everything inside the radio. It's got a separate local oscillator, unlike the little roux, which has the onboard oscillator in this mixer doing the work for you. This is a conventional discrete component transistorized crystal oscillator, and it's driven by an Iambic Keyer, and there are two outputs from this oscillator. One of them drives the mixer directly for receive, and the other one is the transmit output, which goes through a switching stage, the keying stage. This is a standard stage you read about in your basic REE or the license exam, where you don't put the keying stage, you don't key the oscillator, you have a keying stage which isolates the oscillator. This is what this is. This is a switch. So the Iambic Keyer is switching the keying stage on, the local oscillator is shifting frequency, and then the output from the keying stage, from the oscillator on transmit, goes through the PA, through the low pass filters, and out towards the antenna. There is no switching here on receive. So this receiver is listening to the transmit output, around about 2 watts. There are some filters and line clippers in there to prevent it creating a problem, but there is a switch here which has to turn the receiver off, otherwise it would deafen you. That's what's happening. It's quite crude, but it works. So PA stage is up here, its own separate frequency local oscillator driving the transmit side, and then on receive, this Iambic Keyer tells the local oscillator to shift off frequency by 700 Hz, and then it drives the mixer so you can resolve a receive signal through to the audio amplifier. And this bit here is the other half of the LM386 audio amplifier, which has been configured to a very tight notch audio filter. Really clever idea. A nice little kit, and it works extremely well. Let me try and show you what's going on. Now, nothing up my sleeves except my arms. This is, try and follow a little bit, because it does get a bit complicated. So, let's suppose that you want to transmit on the 14 megahertz QRP frequency, which is 14.060 megahertz. So your transmitter frequency, the local oscillator, the TX oscillator, will be on that frequency. It'll be on 14.060 megahertz. There we are. So we are transmitting on that frequency. There's our carrier. And in fact, that's where the carrier will appear from the other guy transmitting back to us, if he's on the right sideband, hopefully. If he's not, you won't hear him. So that is your transmit frequency and the other guy's transmit frequency. In order to receive it, we have to move the local oscillator off by around 700 hertz. This is the tone that you hear when you receive a CW signal, because the difference between the local oscillator and the incoming transmission has to be 700 hertz apart, so the mixer will convert this down and give us a 700 hertz product as an audio tone to listen to. So far so good. So the RX oscillator is shifting off frequency by a very clever little mechanism. Unfortunately, a direct conversion receiver has an image problem because it receives both sidebands. In other words, it receives the sidebands of the receive mixer oscillator. So it's 700 hertz to the wanted signal, and if there's another guy down here that's also 700 hertz away, you'll hear him as well. And very often you will be listening to an image, transmitting back to the guy up here, and wondering why you're not getting anywhere. So you have to be able to know which of these two frequencies you're listening to. Now on the Rooster, it's got a receiver independent tune, which takes you quite a long way. And a lot of people who use these mark the image on here, so they know which side of the receiver is receiving on of the mixer sideband. So you mark it. This is slightly different. Now what this does, it switches the receiver and transmitter sidebands. So now if we flip over the transmit and receive oscillator frequencies, we can now transmit here and receive here. And that's what's happening inside when you alter this little switch on the front. You're flipping the sidebands over. So now we're listening to the lower sideband of the mixer rather than the upper one. This will almost disappear because this is now 1400 hertz away. Very high pitched tone, so you won't hear it. So there's your TX oscillator, there's your RX oscillator shifted. So you'll always get this image problem, and don't forget that you will also get an image up here as well. So once you've shifted this thing, flipped it around, any image issue is going to be up here. Okay, you're following me so far? Sort of, right. So how do we tell which is which? Well, hang on, let me go back, sorry. How do we tell which is which? This switch on the front panel is going to flip these two around. So if I'm listening to this guy here, I'm on the wrong sideband. When I flip this switch over, the local oscillator will move down here. So this pitch will go up in frequency. And that's a clue that I'm on the wrong sideband. If the station is down here, then as this oscillator moves down to this frequency, the pitch will go and disappear. It will net, 0 beat. So I can tell which is the image once I get used to flipping the switch backwards and forwards. So I can transmit on two frequencies, which is sometimes necessary because 14.060 is a popular frequency and it can be used quite busily during the day. So I've got the option of flipping these two apart. It's not much, so it's 700 hertz, something about that, but it's really handy. And you haven't got the faff of trying to decide whereabouts this potentiometer is on the Rooster and try to guess where you are. At least you know you're either on one sideband or the other. That's how it works. This is the oscillator. It's discrete components and it shows its age a little bit. This bit is the oscillator itself, crystal controlled, two trimmer pots here, two trimmer capacitors, sorry, and this little diode. This is where all the clever stuff goes on. So that's the oscillator. Down here, we've got the trickery that flips that carrier over. And it's done with this thing here. So your switch is in this position down here, which takes this logic signal here, and it connects it to the base of this transistor. Or when it flips over, it takes that signal and connects it to the collector. This is an inverter. So it's actually inverting what the transmitter is doing on the keying stage. It's flipping this around. That's how it changes sidebands. How it actually does it, I had to scratch my head a bit in this, because what's this diode doing here? It's not a varactor, a variable capacity diode. It's using something called diffusion capacitance, which is a feature of a diode in forward bias. So this diode is forward biased to ground, and We can't alter the voltage on that point because this will always clamp it to around about, this is a high-speed switching diode, so around that 0.4 of a volt, something like that. So this will always be clamped at 0.4 of a volt. So this is doing nothing in terms of voltage. What it is doing, it's allowing more current to flow through this diode. When the current increases through the diode, the number of charge carriers around the regions inside the diode and behind the depletion layer start to increase. And that changes the capacitance, which shifts this oscillator frequency. And I sat back and I thought, God, that's clever. Somebody's really thought about that, and I really had to struggle to figure out how this worked. I thought it may be grounding this thing out and taking it out of circuit and also. So I spent a lot of time faffing around it. That's what I think's happening, but they don't explain it anywhere in the manual, and I can't find an example of this on the internet. So I'm guessing that's what's happening because I can't find another reason how it would work. It has to be capacitance, and the only way that would shift in forward bias would be diffusion capacitance. It has to be that. But it would be nice to talk to the guy who designed it to find out. It's really clever. Okay, what else we got? Now here we've got, this is the keying stage, yeah, the bit that they talk about in your radio amateurs exam. That's the keying stage. That's the power transistor. That's the RF choke for the supply line, and that goes out to the low pass filter. So that's essentially it. And then this thing here, this is the TX drive. That little pot there just adjusts the output power for the transistor, which you can get from either watt to watt and a half to 2 watts on 20 meters. Side tone circuit has to be generated manually because don't forget we just switched the audio amplifier off from the front end of this transmitter because we're hearing the transmitter. We don't want that. So there's a little audio oscillator. This is collector to base, so this is a phase shift oscillator with just 2 capacitors. It sounds like a tractor. I have to say it's not particularly good. It wants looking at. Whether or not there's a problem with mine, whether or not these want looking at, I don't know, but I'm going to put a scope on it and have a look at the waveform. It looks a bit rough, but it works. You can hear it. And that's the mixer. You've seen this standard NE602 mixer, and they're really, really good devices. So it's two audio outputs, one of which is text to the audio amplifier, the other one is the audio filter. Front end. Interesting part about this is it doesn't switch the front end. There's no transmit receive relay. So your power from the transmitter comes through here. These are the 2 harmonic traps, which you have to wind yourself, and they're quite fiddly. Straight out to the antenna, and on receive, you come down here. These are 2 clipper diodes, limiting the voltage at this point here, and this is the receive chain. And what you've got here are a 2-pole crystal ladder. You've done crystal ladder filters before. You might have 5 or 6-pole crystal ladder for an SSB filter. This is just a 2-pole, but it works quite effectively. It's very good. But there's no switching. So as you transmit, your RF's going back down here, and it's being clipped by these. It doesn't matter, it's only low power, but it's still... Anyway, there we are. Sorry, so these are the 2 coils you have to wind, and they are titchy. Audio filter, this is the audio amplifier. We've got a little FET in here, and this is the one that's turning the amplifier off so you can't deafen yourself when it goes into transmit. So this is interrupting the transmit from the audio amplifier. This is the side tone coming in. The side tone goes out to your headphones when you're on transmit. And this is the kit you can buy independently from Kanga if you want an audio filter. If you've got one of these and you want to add a bit of audio filtering to it, you can buy that separately. That's why I say it's 3 kits in one. What does it look like? You get some goodies. You get all this hardware in the box here. That's your band kit. So that when you specify the transceiver, that's what will come in the kit based on whatever you've ordered. 40 meter, 30 meter, or 20 meters. At the moment, it's hinted there will be others. You get a lovely little magnifying glass, a little Fresnel magnifying glass, free, wonderful thing. It's very good actually. You can see the bits. Tin box to put it in. The pre-populated PCB, that's the band pack, and all the hardware. That's what you get in the kit. And everything that's frequency determining is in this bag here. This little thing here is, I said, an extra £1 for volume control. Oh, that's good. That's what came. It does work actually, it's okay. You use it on here as well, this little volume control. Yeah, £1. You can't even buy the plug for £1, can you? Whatever. £1. Great stuff. Right. This board is showed its age a little bit, so it's limited to 1 watt. Now, in Europe, there are a lot of people who want 1 watt because there are competitions 1 watt, as the 1 watt day and all the rest of it. So this is the little resistor which limits the drive to the PA transistor, which goes in here. You have to get this resistor off. Paul recommends it at Kanga because you get about 2 and a bit watts out, or 3 watts on 40 meters. But it's been soldered in with some pretty crappy Chinese lead-free solder, which melts at about 900 degrees C. So it's a bugger to get it off. You've always got to get a blow lamp on it to get it to melt. So I wound the Weller iron up as high as it'd go, blood it was soldered, and eventually it came off. And that, yeah, it did. It needed something on both ends. Yeah, it did. He just says, put a big blob of solder on it and wait. Okay. Right. So as I say, these are very hot iron, about 470 C, and a big blob of solder, and give it some time. That's your first stage. So once you've got the first bits together, you end up with the local oscillator, which is here. That's the oscillator crystal. That's the drive power limiter, RX and TX trimmers. Keyer is here. This is a little mixer already on the board for you. Audio amplifier and filter is here. And then your bandpass filter for transmit sits in. Sorry, these are the receive crystals. Bandpass on the input, and then the output low pass filters are here. The only problem with this kit is that it's fiddly. If I take this thing out of the box gently, because then you can bend it, won't go back in again. That's it. You see all this stuff on the front panel here. It has to line up with these holes. And of course, it has to go inside the box on a little groove. When if you faffed around in the darkness of your garage and you slid it in, because you can't get to the bottom of the board. So you have to guess. So you attach one pin plug with one pin, put it in, have a look at it, take it out, solder the rest of it, take it out again. Eventually, you've worn your board away, but it is a bit of a faff. But it does go to, it's not bad. The tolerances are pretty damn good. So you have to be very careful that all these bits go through all those holes there. When you get the copper for the low pass filter, it comes in a big rat's nest in a bag, and it's all kinked to buggery. So you do need to stretch it, and this is my wonderful stretching device. You see the state of my workshop. I'm terribly sorry about this, but this is the way it always is. So you have to stretch the wire to get the kinks out. It works. And don't stretch it too hard so it goes down to 48 gauge. Just give it a tug, and it'll be all right. Gently stretch the wire, gentlemen, not too hard. You have 6 bits of wire and no filters. And then this is the tricky bit. Winding these. See the size of my fingernail compared to that toroid. This is not a big toroid. It's about 11 mils in diameter. So the trick with these things is a bit of MDF, 8 mil dowel, put it in a drill, file a point on it. Then just blunt the point, because you will poke your eye out with it, I guarantee. Yeah. So just put a blunt end on it, and then make sure it's big enough to get the toroid and the windings around it. And once you get this thing, you can trap that wire and just work your way gently around, happy as a clam, and it will wind itself almost. It's really easy. Works a treat. So that's what I suggest you do when you're winding any toroid. Put it on a tapered peg. Really easy. When you're doing this, don't do this in a workshop like this. Because you know what's going to happen, do you? It's going to end up behind a dead mouse. Yeah, so we don't want that. So you do this somewhere where you can see the floor. Okay, the toroid. When you wind these things, correct number of turns, 11 turns for the small one. This is the smaller inductor. Leave about 3 to 4 centimeters of wire so you can put another turn in if you need it, or you've got enough room to hang on to it. You don't need much to solder it in the board, but give yourself a bit of room. It doesn't alter the inductance very much. And then you will need one of them, ideally. It does work. It wasn't a million miles out, but it was out compared to the instructions. So it says 11 turns and 13 turns. We'll put you round about where you need to be, and it wasn't. So this is about 80 quid. And if you do a lot of this work, for God's sake, buy one of these things. If you're identifying your little capacitors and you can't read them, this will tell you what it is. Resistance, it will tell you, and inductance, and it's really accurate. This is the Peak Atlas LCR40. It's a really good little piece of kit, about 80 quid. I found on one of my coils, despite the fact that I followed the instructions, it was light on inductance. Now, what you can do with these things is, with a toroid, you can squash them up, increase the inductance, but use your thumbnail and pull them apart a little bit like a concertina, and you'll adjust the inductance 5 to 10 microhenries at the most. The bigger coil was a bit out, so I had to add another turn to that, which is why I left this long leg on here. When you put the coils in, it's a good idea to put a bit of araldite around about here the night before you put them in. Because as you put these coils in, of course, this thing tries to unwind itself and it changes the inductance. So just be very careful with it. The enamel on this thing is supposed to be heat strippable. It does smoke like hell when you put your iron on it, but I do scrape mine anyway. It will strip with a soldering iron. But a dab of epoxy just here. And once you've got them in and it's working, another dab of epoxy around there, because these things can get a bit microphonic. So if you're banging your radio around it, these things are wobbling around, it'll change inductance a little bit. So just stabilize them a wee bit. Alignment's easy-ish. The instructions say first of all, you set up the transmitter. So you use your rig on it into a dummy loader into the outside antenna. Set it to 14.060 and you transmit on this thing and it's miles out. You then try to pull it in with this control here and it doesn't work. So you have to, these are obviously in parallel, so you have to play around with these. That's the RX, that's the TX. So you turn this power down and then you just play around with these. Once you get them in the sweet spot, you know what, because it starts to adjust, then it starts tracking and you get on frequency. He does recommend realigning it after a few days once you've been using it just to make sure it's okay. But transmit first, then receive. So you then set your transmitter very low power into a dummy load and then you tune the receive frequency so you can hear it. That's all the alignment is really, it's dead easy. TX and RX and RF power. Fully anti-clockwise low power, fully clockwise maximum power. I set mine about 80%, so about 1.5 watts. I haven't a watt meter which will go down to 1.5 watts, so I'm guessing, but it's putting out a reasonable amount of power. And there's some interaction between these two pots. You can hear the local oscillator frequency. This is the problem. When you take it out of the can, and this thing is radiating like a chimpanzee at the moment. So as you sit this down next to your expensive Yaesu 101 MP, and you are keying this thing, it's going woo, woo, woo. You didn't get that. So you can hear the local oscillator on receive and the transmit. You don't know which one is which. So you do have to be a bit circumspect in how you align this thing. And when you put it back in the box, it all sorts itself out. It is a bit, so I thought it was chirping at first, which alarmed me somewhat. But it isn't, it's just the fact you can hear the local oscillator. That's it, it works. It does very well. Unfortunately, I was all set up, connected to the antenna, and I hadn't realised I'd been in Aurora the night before, so the bands were absolutely screwed. And I did put a call out, and an HB station came back to QAZ, G, question mark. I couldn't get him, he just disappeared into the noise. So, unfortunately, I haven't had a chance to really try it out yet. But if you do build these things for, pardon me, crash. Sorry. Sorry, Mika. Oh dear. Could be nasty. Anyway, 14.060, there is a regular QRP net, 9 AM UTC on Saturday mornings and on Tuesday mornings. And they're all over Europe. So it's a really good net to get into. And then they'll post onto Facebook, so you'll know you've got them. You want to look at how clean this thing is. It actually is pretty clean. But obviously, if you're winding your own harmonic traps, you want to be making sure that the traps are working. So you stick it on a spectrum analyzer if you have one. You don't need an expensive spectrum analyzer. What you need is one of these. This is about 150 quid. How anybody can make a spectrum analyzer of this quality and this capability for 150 quid, I have no idea. 10 grand, 15 grand for a decent one if you buy a commercial instrument. You can get it for about 1,500 quid if you go to some of these Chinese import places. They aren't bad instruments, but it works. It's really good. And it's a bit slow, but it works. However, care and feeding of your spectrum analyzer. So this spectrum analyzer can do a whole load of things. And it's not really a subject of a talk tonight, maybe later on. But you can select harmonics on the spectrum analyzer. You tell it what the fundamental is. You tell it what the frequency range you want to look at above the fundamental. And you'll see here, it's put a load of blue lines down. Yeah? Fundamental first, fundamental second, third, fourth, fifth, sixth, and so on. And they're all well down. And what it does, it measures the harmonics dBc, dB with relationship to this carrier. So you're not adding and subtracting these numbers. So I'm coming in here at round about neg 22 dBm off the transmitter, which is about right. You don't want to go below, much above neg 10 dBm for a small spectrum analyzer. So about minus 20 dBm signal injection. And all these are in dBc. So this one, second harmonic, where is it? Up here. minus 54.3 dBc down on the carrier. That's pretty good for a two-pole filter. That's pretty good. And it shows that the measuring the inductance and setting them right first time works. And so it's a good kit. It cleans the whistle. I can't hear any of these on my transmitter. So it's very, very good. So it cleans the whistle and you've done your tests. So what's all this nonsense hanging off the end of it? Yeah. Well, you will see on YouTube people getting a handy talkie, connecting a piece of BNC cable to a 30 dB attenuator and shoving it into the spectrum analyzer. Don't do that. Like your mother said, don't do that. No. It's not good practice. The way you use a spectrum analyzer is you use an RF tap, which means that you are driving the transmitter into this box of tricks, which has a transmission line in it. That transmission line is terminated in a 50 ohm dummy load. So a transmitter is seeing a 50 ohm dummy load up here to full transmit power because you want to be looking at fairly high power. You don't want to be looking down in the weeds. What this does is one of my homebrew devices. This is what I call an RF tap, an RF sampler, RF sniffer. And this comes out. This is the probe. And you can make different sizes of these. It's just basically a conductor with a pad on the end attached to a BNC connector. And on there, inside, you'll see there's a capacitive plate. You can get resistive versions of this, but mine is completely decoupled for DC, which these things don't like either. So if there's any DC on it, this will stop it. And you can adjust this for the amount of attenuation you need. So you have an almost infinitely variable attenuator tapping off a sniff of RF, which your spectrum analyzer will thank you for, rather than putting 5 watts up its shirt through a 30 dB attenuator from China, which is probably about 3. So do be careful. Your care and feeding of your spectrum analyzer, they don't like it. Up 'em, Mr. Manning. And you can see here that the third harmonic is almost non-existent, which is pretty damn good. So for a two-pole filter. I'll just put a couple of pictures up. The final part of the slide. This is how you calibrate things. So you've got the VNA, and you take the output into the transmission line. This is a BNC 50 ohm terminator. So it goes through to a terminator. This is the sample sniffer, also 50 ohm terminated, back into the input port of the VNA. And this is what it's telling you. And you would expect this, as the frequency goes up, capacitive coupling increases, efficiency increases. So this is about neg 50 dB at AHF, neg 30 dB at VHF. But I can make a smaller probe, so just swap the probe out if I'm on VHF or UHF. And it's dead easy. Well, it's dead easy to make. If you've got a lathe, it's all right. But you can actually build these things yourself, or just bits of wire if you want, just to protect your spectrum analyzer. And you'll get a far better result because in here is a mixer. If you overload the mixer in a spectrum analyzer, you get sproggies. So spectrum analyzer basically sees rubbish intermodulation products because you've overdriven it. And you've got all these spikes and spurious emissions inside you think, oh, the rig's terrible. It's not, it's a spectrum analyzer, you're overdriving it. So that's what these things prevent, overdriving a spectrum analyzer. Okay. RF tap. My homebrew, yes. I like doing things like this. Bits of metal and shavings and dark nights in a lonely workshop, all of me over the pot. Wonderful, isn't it? It's what I'm retired for. Everybody can go away and sleep below. Conclusions, all right. It's a really nice update to the old Rockmite, over 20 years old. Not really a beginner kit, not something to start off with if you've never sold it before, but it's not bad. And it's an all-in-one QRP transceiver. You plug your Morse key in, whether it's a straight key or a paddle key, it recognises the difference. Straight in there. 1 or 2 errors in the instructions, which I've mentioned to Paul. He's happy with that. Mechanically a bit fiddly, but some additional test equipment's probably useful, like the LCR meter, and very good value for money, 53 quid, which for a fully configured Iambic Keyer CW transceiver is, well, what can you say? It's pretty good. You couldn't buy the bits for that, really, you couldn't. Lots of QRP activity in Europe, around 14.6 weekly activity events. The perfect excuse to learn CW, gentlemen. It is. Not hard, which we're going to talk about in a later talk in May. Learn CW, 12 words a minute will get you QRP off the mark because they don't rattle off. There's no point in going fast with a QRP signal. You can't hear them. You want something slow and steady. And it's standard exchanges. So it's not difficult. You're not talking about your life story and people's dogs and why the Russians invaded Prussia and all the rest of it. You're talking about signal reports. Thank you very much. 73s, yeah. Nice rubber stamp QSOs to get you started at a low speed. So these are really good kits if you're learning CW. And that's it, ladies and gentlemen. It's the Rock Rose. Any questions?
A few slides ago on the spectrum analyzer, showing the harmonics, there wasn't a third harmonic at all.
No.
I'm guessing that's the one the filters.
That's the one the filter's really catching you.
Okay, really well.
Yeah, I look at the gap and I thought, hang on, because it should be something, but no, it was there. Yeah, the third harmonic tends to be the problematic one, so they tend to nobble that one pretty hard. But yeah, it's a really good little radio, absolutely fantastic. I mean, modest test equipment, 150 quid for that, and a few quid for an LCR meter. Could talk about my stick if you'd like, if you've got anything. It's fishing pole, by the way. Carbon fibre fishing pole. I have lots of these top kits. They don't have to make a mess of your hands if they start to break. You get bits of carbon fibre in your hands. But great for outdoing Richard with the longest pokey stick in the world. Thank you, ladies and gentlemen.
Thank you very much.
We really appreciate you taking the time to watch this video. Don't forget to check the video description where you'll find additional information about the video you've just watched, along with links to products used and to the Haddai's website. If you enjoyed this presentation, please feel free to hit that like button. Maybe you'd also consider subscribing and clicking the notification bell so we can let you know the next time we release another video. Thanks again for watching.